Okay, so as agreed, today there is a visiting lecture, and as mentioned earlier, the visiting lecture will be delivered by Dr. Adam Kladowski. Adam is one of the research stars we have in the university. He was holding the position in Academia Finland and applying the follow-up position, and the follow-up position is an Academy Fellow position, which is highly appreciated position. We'll see what's going to happen to your proposal, but he's in that line to get these appreciated positions. Now, Adam's research line all the time being related to biomechanics, one way or another. So it's either human biomechanics or animal biomechanics or instant animal biomechanics. So what we're going to learn today is, of course, biomechanics. So take the opportunity to learn from the guy that knows the biomechanics back and forth. This is an application field, but Adam knows the theory as well. Enjoy.
So, welcome everyone.
And I will be back in my office and I follow this using the YouTube.
Okay, thank you for the introduction. So we'll today have introduction to biomechanics. I'll try to keep it relatively simple. I won't dive into equations because that's what you did with Aki during the course most of the time. I'll just show you how you can use the tools that you already learned to study biomechanics and what you can actually, why do you do actually biomechanical studies at all. So what is the motivation for biomechanical studies? That's the very first question that we have to answer. And one of the motivation is, for example, prosthesis design. If you have a need for replacement of a joint, for example, the picture you can see is a knee joint. On the left, there's the intact knee, or actually damaged knee, but still natural. The cartilage, which is the surface between the bones, is damaged. So then the bones start touching each other, and that causes a lot of pain for the patients. And one of the treatment is introducing artificial elements there, which is shown on the right-hand side. And that's a metal element that should just work as a bearing. And the bearing should have a natural shape. And one of the problems is that everyone is slightly different. Even if you compare, look at your colleagues, you will see that there are visual differences from the first side. But people have different builds. Some are heavy, some are lightweight, some are muscular, some other are not. And the same comes for the details. So if you look at the knee of a specific person, you will notice that every knee is different. And you need to make sure that the prosthesis that you design will fit to the patient. And you don't want to make first the surgery to open the knee, have a look there, and make the measurements, then close the knee, cause a lot of pain, and then do the implant, install it, and then do several refits. It's not a car. It's not a machine that you can actually grind something and insert it again. You would prefer to do one surgery and do it correctly from the first shot. And what you have to make sure, so that people would feel comfortable after the surgery, is that the mechanics stays the same. So you want to have the motion similar. Even though we look at the knee and we think, oh, it's a hinge joint. It's close to a hinge joint, but it's actually not only one axis of rotation. This axis is actually traveling a little bit during the rotation. And people are quite sensitive to the feeling. Sometimes it's difficult to quantify things. It relates also to user interfaces. Like if you have a button to tell whether it feels good or not, you have to press it several times, and people sense it instantly. But as a design parameter, it's difficult to tell what is the spring stiffness there to make it feel good. And now imagine that you have a joint replacement, and it also has to feel good, so that you would like to actually walk instead of after surgery just go on the wheelchair and say, okay, I'm sitting, I'm not moving anywhere, because it's painful, it's inconvenient, and it feels bad. So to do preparation for the surgery, to do the implant correctly, it's important to know what should be the parameters of that implant. What should be the stiffness? Can you vary it in some way at least? Because material choice is limited because you have to select materials that do not cause any problems with the biofluids. and can be installed in the human body and won't get rusty, for example. But the other thing is the geometry, surface roughness, and all the small details which you cannot really see, but they make a tremendous difference in quality of the surgery. So that's one of the needs for biomechanical research. Now, what else we have? This is, for example, implant for the hip joint, which have to be embedded in the bone. And this needle part is actually inserted into a bone using some sort of a cement to bond it together. And while they are done in different shapes and sizes, so that you could choose something that fits close enough, and you embed it in the bone, so that's basically like artwork from the surgeon point of view. He has to insert it, put some cement, position it, and then make sure that it's correct. The key problem there is that the pin is relatively rigid compared to the bone, and our bone responds to the loading in a way that if there's a lot of loading, it starts to build up around, and it makes itself stronger. So when you're exercising, when you're moving around, your muscle gets stronger and your bone follows. So if you're not dosing something illegal, then usually your bone have enough time to follow. But those who kind of overdose different medicine to increase their performance, they can even break their bones with their muscles because their muscle will grow faster than their bone can. And now, in the opposite direction is when you get old and you move less, and basically even the late age is a problem, your bones become weaker. And this is also part of the adaptation. When we don't have a high load, our bones tend to be weaker because it's lighter, so you use less energy to move around, and you don't need such a rigid structure. And that, while in some places this adaptation is useful, for example, when you install an implant, it might be a problem. Because when your implant is embedded in the bone and takes too much load on itself, the bone around it might start to disappear, and your cement or whatever you use for mounting it might get loose. And when the implant gets loose, you need another surgery. And this is a common problem that appears with many people, so that's very important to design the structural properties of the implant, not only so that it would fit, but it also have to try to behave like a bone in a way that it would provide enough loading to the bone around it to keep the bone stronger there. And this is why there's a lot of computation needed to optimize that kind of designs. Then these were the simple solutions which were like pure mechanics. Now there are solutions which contain mechanics but much more complex. So this is one case where they designed a foot implant. So that's the artificial foot. And the idea in the design here was that normally when you're walking or running, you're gaining some energy whenever you have a heel strike, so when you're making a step. And then you regain this energy when you have a toe off phase, so you're pushing yourself forward, so you're not wasting energy. And this is normally done by tendons, muscles, and all the set that you have inside. But once there is an amputee and he doesn't have a foot and needs a new foot, it's difficult to design something. So of course you can make a wooden prosthesis or make it from some kind of a plastic, and it will be possible to support your weight on it, but you won't be able to regain that much energy, and it won't be so efficient walking. And of course it's walking with a limp then. Now this kind of prosthesis can accumulate the energy during different walking phases and put it back on when you need it using pure mechanics. So there's a spring load for storing the energy. You can have similar implants which utilize motors, for example some servos, to help you move. There can be, for example, orthosis on the ankle or on the knee joint, which helps you to move the joint if your muscles are paralyzed, for example, partially. And such solutions need a lot of optimization and a lot of training. And to design them, we basically use the multi-body dynamics, flexible multi-body dynamics, finite element methods, and all the others which are focusing on the biomechanics stuff. Apart from the, let's say, injuries and problems with your body, then of course there's lots of optimization done in sports. This is a simple simulation of the wind flow around the ski jumper who's jumping with a style which was known maybe in 70s. Nowadays everybody uses the V style. But because we didn't know how to get a better drag and how to fly better with those, people were jumping like that, thinking that this is the best option. And with the use of simulation tools, with the use of intensive training, they actually came up with the V-style and realized that, oh, if you change the style, you can fly far more, and you can beat new records. So sports is one of the places where biomechanical studies are very important, and most of the sports utilize them in some level. So it can be optimization of the airflow, so minimizing the air drag in some places and maximizing in some other. It can be optimization of your muscle force or activation patterns of the muscles, or aid in a training that makes sure that you use the maximum power that you can produce, because this is somehow limited. If you play golf, for example, there's lots of studies about golf swing and how it should be done to get the best controllability of the ball and the best carrying distance. And you can actually do that using very little force from yourself by just using the mechanics of your joints and using the gravity. So knowing how to do it properly, developing the technique, can allow you to use less force and get better results. In sports, it's really important, especially when you use maximum of your performance. If you can get extra few points or shave off some seconds from a race, then that is really, really important for everyone. Now, when you design the exercising equipment, it's also not separated from the human. Humans have to use it, and even that kind of a simple Orbitrek came as an evolution of a bicycle, really. And the idea was to synchronize the motion both of the hands and the legs, and to allow to make this exercise fun at once, and at the same time mobilize your whole body to certain motion. And now what you have to, if you would like to design something like that, the first parameters that you will be wondering, what is the crank offset? Like how much it should actually travel up and down? What should be the ratio of the gearing between hands and legs? And those parameters might differ depending if you put a tall person or a small person. And that kind of equipment has to be designed to accommodate both. Because you would like to design one machine that can be used by a 200 kilo guy who wants to lose weight, and it might be used by somebody who is a lightweight, some small lady who just wants to exercise to boost her physical fitness. And to design the equipment in that way, you actually need to do some sort of simulation in that case. Now, rowing device, simulating rowing using the air drag inside the drum. It was quite smart invention if you think about it. Practicing on a kayak is requiring much more effort than practicing on such device which you can have indoors. And the simulation of the drag is quite realistic, and of course the motion is also helping to develop the similar technique that you would use on a normal rowboat. Then there are some fun devices, like this is exoskeleton type of a shoe, which have a big spring that allows you to jump a few meters even in the air, something like that. So you walk and jump, and of course it's not a problem to build a device that will lift you up to the sky, but it's a problem when you're landing, not to break the leg. And somebody had to actually design the spring stiffnesses and damping mechanism so that at once you get a lot of energy back when you're jumping, so you can use the high jumps, but at the same time you need to dump enough energy so that when you're landing you're not breaking your legs. So it cannot be so that you're getting the energy jumping up and while landing it's totally solid. It has to take the energy back, store it in a spring, and then allow you to use it forward. And of course the balancing is a problem, so if you try to design something like that, there's a very small leg support in here. The support with the ground. So of course it has to be in a place where it allows you to actually balance on it, so that when you're standing you would not be falling down. And that requires a lot of trial and error or simulation to optimize that. Now there are virtual crash tests. This is a very common discipline, especially in automotive industry. There are situations where you don't want to put a human and test. It's not the Flintstone type of crash test where you put a guy and see what happens. but you prefer to put a dummy, measure certain values like acceleration of body parts, shear forces, and other properties. And then before you do the actual crash test with a dummy, which is quite expensive thing to do because you have to crash a fully ready car. So imagine if you try to test even a cheap car, it's several tens of thousands that you have to spend on a product and crash it within a few seconds, and then you get some result. To get actual result, you have to crash quite many of them. And if something is wrong, redesigning and trying to do it again would mean that you're off the market quite soon. So what has been done is mostly there are virtual crash tests with the virtual dummies, and everything is just simulated. The car behavior, the way how the body deforms is basically based on finite element models, and they can be more or less accurate depending on the need of the simulation. On the first trial, it might be just a model to tell whether the space is not damaged too much, but then you go to the fine detail models where you really want to know the details where the person is hitting and what kind of forces are acting on the person. Especially it's important nowadays if you think about the Euro NCAP tests and you have, for example, baby seats and you need to evaluate them as well in the crash accidents. So when you design that kind of products, you need to make sure that your product is good enough before you send it for the crash test, because after they do the crash test and publish the star rating, you want to get 5 stars. Otherwise, it's difficult to sell your products on the market. So preparing for the crash test using the simulation makes it a lot easier. Of course, the race cars and any type of performance type of analysis where you can have a crash at really high velocity, that's really important. For example, F1 cars have a specially designed nose to dissipate the energy. The wheels are designed so that they fall off, so that because it's safer if they fall off than if they keep the mass on the car. And that came from the simulation and of course studying a lot of accidents. So nowadays you can see the car being crashed on a race with like 300 kilometers per hour, and the guy gets out from there. And Michael Schumacher is a good example. He damaged himself skiing and he didn't get any problems while racing, at least not that level. So because there was more studies on his racing and how he should do that and how the car should be designed than there is on, let's say, skiing equipment for amateurs. Now, the definition of biomechanics is basically that we apply principle of mechanics to biological structures. There can be animals, there can be humans, there can be cells. You can have different scale level. You can go on the cell level and look what happens with the small things inside our body, or you can go to the macro scale and look at the bones and muscles and some other tissues, which are basically large things. Now, what you've been learning from the Akis course was mostly how to apply the simulation to the man-made structure. So you could simulate an excavator, you could simulate a crane, you could simulate a bunch of different things. And each of that kind of devices have several important things, like it has a control system because you need to know how to move it. It needs to have some sort of a frame to keep the things in, so it's a basically structure of the machine, and it needs to have some actuators that will put the things in motion. Then it can be hydraulic actuator, water hydraulic actuator, there can be electrical motors, there's a bunch of different options available, and they are used depending on the price and quality and other design properties. But now, if you have a human, how do we simulate the human? We can see that there are some similarities. So like in the excavator or in a car, we have some kind of electronics which work as a brain, and this is our control system. In case of human, we have, of course, the brain and nervous system for control and getting the signals from the body. But we have also a load-bearing structure, which are our bones, and that is the same as modeling a frame in the excavator. So if you know how to model the frame, well, you should be able to model the bone, at least to some extent. And there are different material properties, there's different shape, but you can use the CAD tools as well to model bone, similarly like you model boom or something like that. Of course, the shape is more difficult, so it's more complex to model, but you can use similar tools. In case of force production, like if you have an excavator, you will have a bunch of hydraulic cylinders, and there will be pump for oil, and there will be set of valves that control the flow. In case of human, you have muscles, which kind of deal with all type of actuation, and they will just accept the control signals from the brain without needing for like hydraulics. They need some minerals from the blood and oxygen, but they work fine without any liquid actually doing the work. So now what we have next. So if we look at both systems, well, either man-made structure or a human or animal or something like that, you always can convert it into a mathematical model. And that's the core idea in the biomechanics. So you look at the structure, you try to divide it into smaller and simpler pieces, and then connect them with something. So in case of an excavator, you have, let's say, a bucket, an arm, and some other parts, let's say the main structure, and they are connected with the rivet joints, so they allow rotation. Plus you have actuators on top of that move those structures with respect to each other by applying forces. And of course, when the excavator is digging in the soil, the contact force between the bucket and the soil will be transmitted back through the actuators and through the structural elements to the rest of the excavator. And if some forces were exceeded, then some elements are breaking. Either it might be the actuator that breaks, it might be the hose with the liquid under pressure, and it might be a structural element that simply breaks because it's overloaded. Now in case of human, we have similar thing. We have bones and muscles, which are separate, you could assume rigid parts. And if the muscles are working properly, you can actually do some job. And while you're doing the work, you get a feedback back through your sensing network, which is basically nervous system. And you feel whether you're overloading yourself or not. But still you can get damage if you're overloading something for a long time. Like in case of machines, you can get a fatigue damage after a long time. So you first apply the load and it seems that it's okay. You apply it the second time, it seems to be okay. But after 100 times, something is cracking and breaking. The same goes with a human. So if you have a straining job and you're moving some heavy elements, then first time you lift it, you move it, feels heavy, it's okay. Second time you learn how to do it, feels heavy, it's still okay. But after some time you get some kind of injury because you did it the wrong time, or basically there's a fatigue crack accumulating somewhere in the bone because you're overloading for a long time. And to avoid that, we need to have some sort of a model. So now, if we look at the both pictures, we have the structural elements, which we represent as bodies in our mathematical model. So they can be rigid bodies, for example, or flexible ones. Then every body has to be connected to some other body, either by forces or by joints. Basically, joints always represent also some kind of force connection. That's how it's modeled in mathematics. But on our kind of a higher level, we represent them as joints which restrain some kind of degrees of freedom. In between, we can have some spring elements and damper elements, both modeling a machine where you have some compliance, and it can be modeled as spring and damper system. Similar in human, if you have a tendon, for example, which acts as a spring and also as a damper, you can model it the same way. So using the same mathematical models, you can model both excavator or a human. Everything after you get this kind of conceptual model with all those elements has to be converted into a math. And these are the equations of motions that you probably know by heart already from course. And basically you have the mass matrix, you have the velocity vectors, you have stiffness matrix, and the damping matrix. And all of that combined allows you to solve for different quantities. So depending what you know and what you don't know, you just solve. So you could solve for forces, knowing, for example, motion, and knowing some other elements, or you could solve for the motion knowing the forces applied to a body and knowing the inertial properties. And it's up to your needs what you are going to solve from there. So mathematically, there's no difference whether it's a human bug or an excavator or a car. The difference is in the modeling and your understanding of the of the concept. And of course, model parameters will be different. So if you model car suspension, you will have a spring stiffness, which will be probably several thousand newtons per millimeter. But if you have a muscle stiffness, the values will be much lower, unless the muscle is loaded. And of course, if you have some kind of curvilinear relationship between properties, there will be just different curves that you will use. But the general model is kind of similar. Now, let's say that you look at the knee, and you can model it as a hinge joint. So that's one of the simplest approaches. So you build one beam in your software for simulation, you make another beam, and you apply their properties. You don't really care about the shape in that case. You care about the inertial properties. So the center of mass for every part is important, the total mass of the part is important, and then moments of inertia are also important in terms when the part is rotating, so that it would know how much resistance it's causing and how much torque or force you have to apply to move it. And the hinge joint you can constrain using simple equations, and it seems like a good approximation. And if you study, for example, walking, and the knee angle is not really changing much during walking, you just have a few degrees that you're straightening the leg and bending it, that will be a fine assumption. But now if you try to study somebody who's doing a squat with a heavy weight on his back, or even sitting down and standing up, then you bend the knee 90 degrees or even more, and then you straighten it. And in that case, hinge joint might be still okay, but might also cause a problem with your model. So what you can do then you can go to a little bit more accurate model, and you can have two surfaces, they are marked yellow in this picture, and those two surfaces will be used for contact. So they will be sliding on top of each other. So if you model the shape of those surfaces reasonably, then you will get a sliding joint that should behave more or less like a leg. Then, of course, those two surfaces won't keep touching each other by magic. So you can either apply a constraint that is actually causing them to stay one on top of another, and that will be some sort of approximation. Or you can connect them with springs that simulate ligaments. So the middle one are cruciate ligaments, and then there are medial and lateral ligaments. Medial direction is usually the middle of the body, and lateral is the outside of the body. That's the naming convention. And if you model it so that there are two contacting surfaces and there are springs that keep it together, then you get something which is similar to the leg model. So if you try to pull it apart, of course the springs will allow to pull it to some extent before they break. So having that kind of model, you can already calculate the forces in the ligaments and see if certain motion would not overstrain them. And that's one of the benefits. And of course you can actually twist the leg as well, even though this twisting angle is usually not big, and it is somehow related to also the bending angle. You can still model it, and you can see how it should be. You can compare the reality and simulation, and then you can fine-tune your stiffness parameters and other parameters. So this is similar, like in case of a man-made structure. You can model a hinge joint using just constraints, or you can have a pin, a contact surface, you can have clearance, depending how much detail you really need for your simulation, and whether you're caring about the stresses on the pin in the hinge joint, or whether you just need to know the overall force that passes that joint. You will choose one model or another, because it's related to computational cost. If you have more accurate model, first of all, it's more difficult to make this model stable, because it's very easy to draw something, but it's more difficult to keep it in place and make it behave as it should. And secondly, when there's lots of additional points to evaluate and lots of contacts, then your model will start to be slower. And depending whether you want to do one simulation and you're happy, or you need to do a lot of iteration and you want to do some sort of optimization, it might put some constraints on where you can run it, whether one computer is enough, or you need to use a cluster, or you need a supercomputer for a very complex model. Now, what kind of methods we have in biomechanics? In general, we have experimental and computational methods. For the experimental, we can always analyze motion. This is something that is really old. Since the beginning of photography, people were interested in photographing people in motion, animals in motion, and seeing how we really move. So pictures of a runner whenever high-speed cameras were developed, or there was a possibility to take several pictures in a row to see how the movement looks for a sportsman and untrained person. This was done a lot. Nowadays we have more equipment for analyzing motion, like for example, we have motion capture equipment that can capture the motion and then we can analyze it later on a computer. We can measure external forces. So if you're walking, you can have a force plate on the floor, and while you're walking you can actually detect the force. And you can have only the vertical component, but let's say see the distribution of the force under your soles. Or you can have a system that will measure the force in 3 directions plus the torques, and it will give you location where the center of the force is applied under each leg, but will not give you the distribution of the force. So these are the options that are currently available. You can monitor muscles activity, so you can attach electrodes to the skin and record the signal, and that will tell you something about how muscles are activated, though it's not a simple relationship between the signal and what is muscle doing. So if someone thinks that, okay, we'll measure the muscle force somewhere from the thigh and I will know what is the force that the muscle is producing, so first do some scaling and then realize that, okay, once the signal is, let's say, 10, and we get a force of 100 newtons, the other time signal is 5 and we get the signal of 50 newtons, so I think I have a curve. And then I realize that I again have, let's say, a value of 10, but the force is no longer 100 newtons, but it's like 150. So a big drift, or I get a signal that is oscillating and I don't know how to interpret it. So it's not clear how to use the EMG directly to convert it to muscle forces, but it gives you some kind of ballpark of what you can do. You can measure other quantities like oxygen consumption. You can have some mask and measure the oxygen consumption. You can measure the heart rate. You can measure lots of body properties from the medical perspective and try to get something out of that. Well, the benefits of the experimental methods are clear, that you get the result. Basically what you measure, you usually get the measurements relatively simple and easy to interpret. So if you measure the ground reaction force, you know that it's a ground reaction force and there's nothing to it. If the person is wearing extra clothes or extra equipment, then this is added weight and you can kind of compensate for that. So that's why it's relatively reliable and easy to interpret in most cases. But the limitation is that sometimes when you do the measurement, you have to be in a certain place. For example, you have a bulky measurement equipment and you're not able to move it somewhere. If you want to measure, for example, somebody walking, of course you can take him to the lab and ask to walk over force platform, put a bunch of cameras to record his motion, and you get some result. But now imagine you want to have the same person and you want to record him during, let's say, play, like a football game. And you would like to have every soccer player recorded, see his motion, and record the ground reaction force. It would be really difficult to put ground reaction force all over the soccer field, because first of all of the cost, and secondly it would change the properties to which the guys are used, so of course they would behave differently. Secondly, for motion capture, when you have lots of subjects, there are also some problems because you might not see all the markers, or you have to use insane number of cameras. So there might be a big cost. It might be a practical limitation of doing certain measurements, and there we have to jump to computational methods. And the other thing is that there is a safety issue sometimes. So sometimes you would like to see what happens if the guy falls off the window. So you can of course find a volunteer who will jump off the window and see what happens, but that might be problematic later on. But it's much better to actually use a simulation for that and see whether he will smash his head or he will just get a small bruise. And in case that somebody has the accident, you know more or less that, okay, this window does not have to be protected because there's not much problems. Or if you see that the problems are severe, then you know that, okay, I have to put some protection there because, let's say, the machine could damage a human or something else. Now, what we do in the computational methods, the simplest way is to do some statical analysis. So you just take a human posture, you assign some weights to different body segments, you assign some pose to the human, and then apply some forces and calculate what are the forces in the joints, what are the static forces, for example, in the ground contact, or in any other place, whatever is interesting. That's a simple thing, and you can do it even on paper. It's a little bit tedious, but you can do it. Then you can do kinematic analysis. So from the static pose, you start moving, And from kinematics, you can either look at the range of motions, you can see if somebody is reaching the limits, because for example, if the sport is happening fast or some other activity, you might not notice that somebody is going over some limits. Like if you play tennis or something like that, whenever there's a ball being hit, there's an impact, and you would like to know something more about it than just looking at static pictures. You can do finite element analysis, and that allows you to get the information about stresses. So how much some parts are loaded. And of course, this is good in a static case. You can also have some simulation in the finite element software, but that will be quite computationally expensive, but it's possible. You can have multi-body dynamics, which shifts from a model like compared to finite element, when you have lots of elements that you have to solve and small time steps and really small time zone that you can analyze. So to analyzing something that can last even hours or minutes, but you have small number of actual variables that you're solving for. So you have some amount of bones, some amount of external foreign objects, and you're solving what happens between them. And if you combine finite element and multibody, you can get the mix called flexible multibody dynamics, where you have some elements which are used to determine the stresses, where you are interested in the stresses, and those models are finite element based, or some kind of model reduced finite element models. And you have rigid elements which do the rest, so that you could see how the dynamic loads are created and how they behave. Now, clear benefits from the computational models is that you don't have really limits on the measurable parameters. Like if you do the experiment and you, for example, want to measure a certain quantity, you have just some amount of skin place where you can attach certain markers or sensors. So if you run out of the space, you're not able to put more sensors. If you have a sensor that can scan some surface and give you some property from there, of course it's fine, but it's usually limited to some range. If you think about the computational method, if you can get stresses on a node, for example, any node from the finite element you can reach stresses. There's no limits, there's no hidden node, there's no node difficult to access, it can be internal node, there's no problem. From the human, if you want to do the measurements, what you do outside is one thing, but if you want to see what happens inside, then it starts to be difficult, because either you cut the person somehow and insert some sensors underneath, and then you hope that it does not affect the normal behavior, or you have to do just the analysis of what you can see from outside, and then try to guess what's happening inside, so interpolate, make some models and predictions. So access to internal parameters is a clear winner for the computational methods, and basically they are non-invasive, so you can simulate whatever is dangerous, whatever is not ethical to do with a normal human being or a living organism. But of course the limitations are also there. So one of the limitations is that you actually model something. You don't have a real human, you have a model of the human, so it's a simplification. And if it's a simplification, you had to cut corners. So if you modeled, let's say, bones as rigid bodies and you have some certain inertial properties, they might be more or less, your model might be more or less sensitive to those. And let's say inertial properties are not that big of a problem if you get them within the reasonable values. But there are other properties that might affect a lot, like for example spring stiffness for the muscles or tendons. If you overshoot them or underestimate them, then your model might behave weirdly. You can walk like on the moon, or you can fall down while standing, not having enough forces. So some parameters are really critical, because they might change your results. And establishing those parameters, usually you have to use some sort of experiments to get some measurable quantities, and then you combine those both approaches, computational and experimental, to get something working. And of course, some models which contain a lot of detail might be computationally heavy. And while solving the problem which is computationally heavy is one thing, we have computers for that, and we can run them even in multiple computer like a cluster, or you can use a supercomputer. That's manageable, but actually creating a complex model is a big problem. Because once you create it, if you include a lot of phenomena, you usually need experts from different disciplines to give you some input, and then whenever you run the simulation, you get errors, and you have to analyze some more insight to the problem. So that's like practical limitation. These are some example of experimental measurements, just to give you an overview like how much limitations there are. And on the top left, you have a sensor that can be installed in the knee, and it works instead of a cartilage. And that's a sensor which has wireless communication and actually takes the energy also wirelessly through a coil. So it allows to install this implant to a patient. I think that there were 2 patients installed with such implants, and then there was data acquired from those guys. And they were able to walk, they were able to do certain activities, and during doing these activities, the data has been recorded for the forces in their knee, which is something that normally you cannot do. But if you compare that, now if you think about it, this is the force from the artificial knee in a real person. And if you think about what would be the forces in the same person being healthy, there might be a big discrepancy. And nobody is able really to tell what would be the force, because for the healthy person, we don't have a way to get inside and measure. But that gives us some kind of information what we can expect there. So if we do the simulation model, we can calculate and we can then cross-correlate to see if it makes sense, whether we are close enough or not. Then the next picture on the right top, there are some force sensors also on similar device with the cables coming out. So that's for cadaveric studies. So you basically take a bone from a dead body and prepare it properly, install it to a robot which will move it just like it's a real bone, and applying different forces that you can estimate, for example, from a multi-body model, you can see what would be the stresses in the joint. And these kind of studies on dead bodies are also carried out, and they provide some information of how this basically confirms. And once you, for example, do such study, the next step is to do a computational model that will simulate and kind of tune it to the values that you measured, and then you can use the computational model to another situation which you don't study directly because it's impossible, and you can get some sort of results. Now here on the side, on the bottom, you have a sensor which is in the hip, and that's a hip joint also with a sensor which has induction coil for feeding the power to that sensor, and it has wireless communication of the data, and it measures forces and torques in the hip joint. So also something like that has been made and has been tested, and because it doesn't require to have batteries inside, which would be dangerous, it could be installed to a patient, then the power can be supplied from the outside with some reader, and the patient can live with that implant later on without much choices. So the implant was probably 100 or 10,000 times more expensive than the usual one, but allowed researchers to get some information about hip forces. And then the middle bottom is the cadaveric specimen of a bone with the strain gauges attached to it. So that will allow you to see what are the stresses on the surface while you're loading the cadaveric bone in some kind of tensile testing machine or a robot that moves it like walking path or something. And then you can see what are the stresses there. And then knowing those stresses in the few points where you can actually install the sensors, because if you install, let's say, 200 sensors on top of that bone, even the cable's weight will affect the results because they will be pulling everything down. So you should have just some amount of points that should not affect the reading, and then from those you compare it with finite element model, fine-tune the finite element model, and get some properties of the material or the modeling technique that you're using for modeling the body. Now, motion capture, that's one of the examples from Jyväskylä. We had a subject where in the reflective markers there was a black background because we use the visual cameras, normal cameras, to track those markers, how they move. So we wanted to see markers and black. And the easiest way was to put the black background and black suit on the guy, and reflective markers with lots of light. You could read that. Then the guy had on his chest something that looks like a bump, but this is actually measuring equipment to measure muscle forces. It was recording the muscle forces from the muscles. So under the suit he has a couple of electrodes on the legs, so we can actually measure his muscle activity while walking. On the floor, the green carpet hides actually a force platform that measures the ground reaction force, and from that we can get quite a lot of data. And on the right-hand side is the whole junk that needs to be connected to actually get the data. Just to give you a visualization that if you try to do it somewhere else, it starts to be difficult because either you have to have a truck driving next to the guy with the cables and you could record this outdoor, for example, jogging activity in the nature or something. That shows that there are some limitations when you want to do it somewhere else. Then there's another machine for exercising, when the guy is just stretching his legs and then pulling the seat, which is sliding up and down. We can change the inclination. And what he has on his thigh here on the bottom is that there's an ultrasound device just attached with the bandage from outside, so that we could see how muscle is moving while he's actually applying force and moving himself up and down. And then on his legs there are a few electrodes to measure the muscle activation signal. And then changing the parameters of the experiment, you get a bunch of data that you can later on interpret and see how it happens. So this is like non-invasive experiment. It doesn't hurt really, except you need to shave your legs, which for boys was a little bit surprising maybe. But other than that, simple experiment and quite a lot of data that you could analyze. On the right-hand side, there's a torque sensor. So basically, you can measure the torque that you can create with the foot. So just like pressing a gas pedal or something like that, you can see how much force you can actually produce. And again, there's an ultrasound device on the leg to see how the tendon is actually behaving during that activity. And the machine was measuring the torque. So measuring the torque, you can then recalculate it using the geometry, what would be the muscle forces that cause that motion, and you can create a model based on that. Now, motion capture is something that is really used a lot. This is an example of motion capture already using the infrared cameras, so there was no need for a black background. And there are just like photocells at the beginning, at the end. When the guy crosses the first photocell, recording starts. When he crosses the second one, the recording stops. And of course, we need to synchronize data from all the systems. So one system is for motion recording, one system is for force plates, one system is for the EMG, which is the muscle activation pattern, and then there might be some additional measurement taken, and they have to be taken with the same timeline, so you can actually see later on when you analyze when it happened. That's the overview of the lab that we used in Ivascula. So this was when there were cameras which were using the visual light. So there was black background, there were photocells, there was a lot of lights around so that the cameras could work at high frame rate. We were aiming at 50 to 100 frames per second. And there was also some synchronization light that blinked, and then you could see that blink on all the cameras. So when you had independent recordings, you could actually align them in time when they start so that you would know how to interpret the data and convert that to 3D. Now this is a setup for the motion capture. There's a human body shown with the markers. The markers have names which are derived from the places where they are located. So toe for the toe, HEE is for the Achilles tendon basically, ankle joint, tibial marker, knee marker, and so on. So they have kind of abbreviated names just to make them relatively easy to use in a software. But there are a certain set of marker sets or location where you should place them, where you get the best accuracy of the motion capture. And this is one idea, how they can be located so that they would not be occluded too often, and so that you could actually track position of every body segment. So you can see that, for example, on the foot you have 3 markers altogether, and that allows you to give the position and orientation of the foot in 3D. Then on the tibia, so the lower leg, you have just 1 marker, but that's enough. When you know the foot and when you know the knee joint location, then this marker will tell you what is the orientation of your leg, and that's enough. You could have a few other markers there and you would get some redundant data, which is always a good thing, but it's not strictly necessary. And the same thing goes for the head. There are a few markers on the head, a few markers on the other body parts, so you can actually track the body motion. And there are locations where you can attach the markers closest to the bone usually. Because if you attach it to the skin, then while you're moving, you could see that your skin is moving as well. So if you take a really skinny guy and make a recording and attach the marker even on the muscle part, the muscle will be moving, so the motion from the muscle is kind of difficult later on to separate from the motion of the bone, because that's the motion of the leg. So that's why the landmarks are selected which are close to the bone, really. This is something that is good to keep in mind. Now, you get some amount of recording. So you set a lot of cameras. You can have 16 cameras, you can have 4 cameras. At minimum, you will need 2 to have a stereo vision where you could track something. But with 2 cameras, the problem is that you will see some of the markers and some will be invisible during the motion. So if you have more cameras, then if you see every marker on at least 2 or 3 cameras, then you can actually extrapolate its 3D or position in the space. And that allows you to do something with that. So once you get the recordings, you have to have the camera calibration. So each camera has a focal length, and you can have wide or narrow angle. And depending on that, the transform from the real world to the 2D space that the camera is seeing can be done. And of course, then you can do the transformation the other way around, having the image from different cameras and having the corresponding points. So if you know where the point is located in the pixel coordinates on every camera, when it's located in a certain 3D location, then you can actually create matrices that you can multiply to get the transformation matrix between camera coordinate system, so the screen coordinate system, and the coordinate system which you place somewhere in your laboratory where you're doing the experiment. And this can be done automatically or manually. Older systems use it manual, newer system can do it pretty much automatically. Usually the calibration goes in a way that you have an object which have certain pattern of points that is kind of difficult to make a mistake, and you move this magic wand all around the volume where you want to record, and the system is recording the motion, and because it knows the distances between the points, it can calculate locations and so on. And after it gets the calibration data, then it can actually pretty accurately calculate where the marker is. If you just throw a single marker in the space, it will know where it is and it can track it. Now, after you have this correspondence points assignments, you have to actually keep tracking. So you have to first get where the markers are, and usually you start with the T-pose like this, because that's a very simple pose for the human to distinguish that where the hands are, where the legs are, and how they are oriented. And when you start with the T-pose, the system gets where the markers are, or it knows where it's expecting to find markers, and then it can name them. And then once you start moving, frame by frame, the system tracks where each marker is moving. So from one frame to another, it moves not very far away if you have 100 frames per second, or even more. So it can keep track of all the markers, and knowing where they are moving, it saves you the data that you need and converts for every marker, calculates the 3D coordinates. Of course, it might happen that, for example, when you're moving like this, when the marker is on the inside of the hand, at this point it might be invisible. And if it's invisible to all the cameras, it disappears and then it appears back, then the system have to recognize, and it might find which marker it is, but it might also get confused. If there are multiple markers in proximity, it might get confused, and then you have the manual work of saying this was this marker actually which disappeared. And that's the part which might be tedious to correct the motion data once you get it. So it's really important to get the marker protocol that allows you to avoid situations where the markers are disappearing. Of course, depending what you're capturing, because sometimes you might have some other objects that might shadow your markers. Now, what we can compute from the simulation models. One of the things that is really important is muscle activation patterns. If you see, so it's not the actual muscle force, but you just know whether the muscle is activated and how much. In a scale, for example, from 0 to 1, which you can say that, okay, 1 is the maximum force, 0 is no force at all, so the muscle is resting. That's something that you can compute, and knowing which muscles are activated and when gives a lot of insight on how we are actually stabilizing our motion. If I'm standing right now, theoretically I should be stable without using much muscle. I should just lock my joints somehow. And to lock them, I actually have to use muscles on 2 different ends. So one muscle is trying to, for example, bend my knee, while the other muscle is trying to straighten it. And because they work in a certain amount of forces against each other, they can actually stiffen the joint. That's the effect. And that's how the joint is locked, and I'm able to stand. But if you try to stand on one leg, for example, you'll notice that it's difficult to stand without moving. You will be actually twitching your muscles quite a lot. and changing your muscle activation patterns as you get tired. So that's also one interesting study to see how we are actually changing, because we have more muscles per joint than we need. If you think about a crab, it has one muscle for bending, one for straightening, for every joint. So it doesn't have much choice to do that. But for the human, you have several muscles to bend the knee and several muscles to straighten it. And it's up to you which one you activate and how much. So you can activate all of them at the same time if you want to, which are doing the certain function. You can also have antagonistic effect when one muscle is trying to bend the leg while the other one is resisting that, so that you would have more control and making a smoother motion. And this is something which is really complex because of this redundancy. So that's why the muscle activation patterns are interesting part of research. Once you can scale the pattern with the external data, so you know what the maximum force is, then you can actually get the muscle forces an absolute value, so you get a value in newtons. Then you can have also contact forces. So when you're walking, there is a contact force between your feet and the ground, and which is interesting to see how it goes. If you have more accurate model, you can have actually the pattern of how the contact points are located and how you move the balance between, for example, lateral and medial side of the feet and foot and what is happening to them. If you're holding some object, then you have a contact force between your hands and the object. If you're punching something, then of course you have contact force between your fingers or your hand and the foreign object. And it might be interesting. For example, hitting something is a good example of accident simulation. When you have a pedestrian, for example, and a car hitting in the side or from the front, and then you see where the force is applied, what is the magnitude of the force, and you can estimate what kind of damage can be created. So that could help, for example, to reconstruct the accident when the police tries to figure out who was guilty. So they could do the simulation and actually see if the version from one guy or the other guy makes sense physically, what is possible. Joint loading, important especially in sports and training. If you know what kind of joint loads you have during activity, you can optimize your training program to maximize the performance of your muscles, but try to minimize the joint loading as much as possible, because your joints have certain limits, and when you feel the pain, it's already quite late, usually. So it's better to know beforehand that you're overloading them. Bone loading is important in terms of simulation of, for example, fracture healing, and bone loading is important if you have people who have brittle bones and you just want to know whether certain activity is dangerous for them or not. So if you know that this is close to their bone endurance threshold, you know that this is too straining. And it's not clear to say, just looking at the person, if it's too heavy or not, because sometimes you can have a lightweight exercise, but performed hundreds of times can cause a fatigue load as well, like a straining exercise done just once. Strains and stresses within bones and within muscles. That's important and interesting, both in terms of designing of implants or just for the knowledge of how the human body is behaving. And fracture healing, this is also an important thing, because once you break a bone, then when the doctor actually sets it so that it would heal and puts it into a cast, sometimes it happens that you have a cast for a certain amount of time, and after that they try to remove it, they test, and then there's still fracture, it's not healing. And that happens sometimes if the external structure is taking too much loading from there, so you don't induce any forces there, and then the healing process can be disrupted. So knowing the optimal stress ranges for those is also important, and so far I don't know if I haven't heard that it would be used in practice, but there's lots of research on that to see what are the optimal conditions for fracture healing, because even the doctors are not 100% sure how to fix it, except some kind of templates that they use, so that it would be best. So the templates are based on experience and not so much on the simulation so far. Now, how do we do the model of the human? First of all, we should have some skeletal model. Usually we start with the skeleton for overall body movements. And we can take some averages. And if we have like height, weight, gender, ethnicality, and age of a person, that narrows down a lot of parameters And we basically are somehow similar. If you see a person in the dark, you can see that it's a person, not a moose or not a rabbit, because we have similar body build, similar structure. There are differences in some body segment lengths and some proportions, but in general, if you assume that you have some kind of a model of, let's say, Caucasian woman, you can scale it up and down for different sizes, changing just those few parameters. Now from that, when you generate the skeletal model, you have just the bones. They might have the look if you have the graphics, but the graphics is not that important from the perspective of the simulation. It's important from the perspective of visualization. So when you analyze your results, you want to see whether, let's say, there's something wrong happening with the model, and it's easier when you have the real graphics than if you have just a rod drawn between two joints and see that, okay, it's moving. So that kind of skeletal figure is also used in some research, but if you can use the real geometry, it's really great. It doesn't have to be too accurate though. Now you can cover the skeleton with muscles, and in this case there are simple muscles which basically join, every bar is basically a force component between 2 points. And that kind of model is really great and works for the situations where you're not using full range of your joints. So if you're bending or something and the muscle goes in the shortest direction, that's more or less okay. But for example, for the knee, when you bend the knee like that, and if you have a muscle attached here and here, then what can happen, this muscle might go through the joint. And when it goes through the joint, then instead of extending the knee when you compress it, it will actually bend it forward. So in that case, you need a joint or the muscle model which will actually bend and slide around the joint, and that means a little bit more complexity, but it's also available. Now what you should consider modeling that kind of human, this has over 100 muscles attached. You can attach more to have actually the full musculature of the human, or you can attach less. And depending on the level of detail that you put to the model, whether you model the whole body or you just take, for example, arm, if you're interested in what happens with the arm, that decides how much time you have to spend on preparing the model, how much simulation effort it will take for the computer to simulate it, and what kind of results you're getting. Sometimes it's not worth to take the full body if you just make a motion of a hand, for example, or the leg in some support. Then the whole body is a kind of overkill. Unless you know how to do it efficiently, then of course it's fine. But if you're just experimenting and try with a small part. If you try to simulate a hand, just take the hand and try with one finger. After you get one finger working, add another one and another one, because otherwise you might get into more problems in solving what is not working in the simulation than actually doing the simulation. Then muscle geometry and model, as I mentioned, if the muscle can wrap around the joints, you can model the full body motion and full joint flexion extension. If you don't model the muscle like that, but you have just some straight line of action, then you have to be careful, because you might get the situation where extensor muscle becomes the muscle for compressing or moving the body segment in the opposite direction, and it's quite easy to get to that situation by accident. And then you have to decide also which bodies you model as flexible and which should be rigid. Flexible muscles or body parts will give you information about internal stresses, which is quite useful, but there where you don't need it, you should use just rigid bones to support the body, because it's a computational expense, and of course it's a preparation time for building the model, which is elastic. That might be an issue. Now, how we build the human model, we have several components. So first we do the anthropometric measurements, so we measure the body size. We need to know how much the guy weighs, what are his lengths of the body segments. They usually follow some proportions, so if you know the overall dimensions, that might be enough, but if you want to be more precise, you can measure the arms and some other details. Then you can add to the skeletal model, which you get flexible bones, there where you want to have stresses. There you have to also create joint models, because of course when you have the skeleton, it's just a set of bodies which can fall apart when you run the simulation. So to keep this together, you have to put some joints. And for the joints, you can have models which take into account also the range of motion, because if you put a hinge joint, well, you can bend it in simulation 180 degrees or 360 degrees, you can rotate it constantly. But it's not a wheel that we have as a joint, for example, in the knee, but it can just rotate certain amount of angle. Some amount in plus, some amount in minus, and you should not exceed that. So it's good to have some kind of a model. It can be a torsional spring that increases the stiffness non-linearly when you reach the limit, and that's how you can model it in simulation, that there's a limit and you cannot pass it. Or you can use some other tricks depending on the simulation software that you're using. When you put the muscle models, it also is not that simple as only how it's the geometry of the muscle, but also how you compute the force in the muscle. You can use a simple PID controlled muscle, which will just take into account what should be the body segment angle, for example, angle in the knee or angle in the wrist, and then it will just apply the force to get there within the time frame which is given, and that is fine. But if you have some dynamic activity, then you might realize that this model might produce overly large forces to initiate motion or finalize the motion, and in that case it's better to use a model which is based on phenomena that are happening in the muscles, and one of the popular ones is heel muscle model, which links the forces and the motion of the muscle, taking into account a couple of extra activities. Then you have some contacts model as well. So for example, ground and feet in walking. If you're pushing something, then there will be some contact on your hands. If you're colliding with something, then you can have contact also in your head, for example, and the foreign object. If you're getting hit by something, there's lots of possibilities. Now, how to get the bone geometry? Because that's one of the tricky parts. And one of the easy ways is to put a person to a computed tomography or magnetic resonance imaging. And both methods are quite fine. They have certain differences. Like, if you try to take the MRI of a leg, so the leg might be, let's say, 0.5 meter long segment, I mean just the lower leg, for example, it will take you around 40 minutes to 1 hour or maybe more to scan it. And during that time, the subject should not move at all, because if he moves, then you have a part scanned and then the other part is offset, and then you would have to correct it, and that might make more trouble than it's worth. So that's problematic. And the other problem with that is that you don't get any information about density from the magnetic resonance. It will just tell you where the bone is, where the soft tissue is, and more or less the information. From computed tomography, you will see the bone clearly. You will do whole body scan in few seconds because it's quite fast method, but you will put a lot of radiation to the patient. Well, a lot. It's not that much, but it's a matter of ethics, how much you want to put radiation to someone who you just want to use in a study, and there's no actual need for medical examination for the person to do some detailed scanning. So radiation versus no radiation, but longer time. And with the radiation, you also get the added benefit with the CT, that you get the relationship of the CT values for every voxel that you get is correlated to actual density. So that's additional information that can tell you something about the bone material. So it can be beneficial to get the CT. Now, from what you get from that medical images, I don't know if you have seen them yourself anyway, or did you have any need for having a CT or MRI for your own needs or medical needs, but you will see something like you can see here. So they are basically slices, and they can be sliced in any direction, because once they get the data points in 3D, then they can put the plane of slicing however you want, and the doctor can look at different slices and see what they say, or what they want to see. And for medical reasons, usually they make slices separated by centimeters even from each other, and then the resolution is just as high as the apparatus is giving. But for the need, if you want to reconstruct the geometry, you might want to have the slices much closer, like in the range of millimeters from each other, to get a good resolution of your shape. So now you get this set of black and white images. Of course, the color profile is something that you can choose. You can have from red to blue, you can have it colorful, but the colors mean just the value of density. So The easiest way is to have it black and white, but you can of course use some more colors if you want to emphasize some differences, and some programs can actually do it for you. So you have to do the segmentation. So you have to kind of draw the contour of the inside of the bone and outside of the bone for every slice. And you will have around 1,000 slices for the bone, like tibia. And from those 1,000 slices, you have to extract those contours. Partially, it can be done automatically with image recognition features, which can trace it. You can have threshold for a certain value, which will detect where the bone is, and some smoothing function. But in the end, there will be some manual work as well to fine-tune it. And once you have the set of profiles that build up your geometry, you can fit a surface on top of that. So you can have the external surface and internal surfaces if needed, and that can do a CAD software for you. And there you get your 3D geometry that you can use in finite element software for meshing. And you can mesh also only the surface, assuming some certain thickness of the wall, which is quite simple approach, but not very accurate. Or you can actually mesh the volume. And when you mesh the volume, you actually can take care of the differences in the bone wall thickness. So this is a simple example where we have fibula and tibia. The fibula is rigid and the tibia is actually meshed. The mesh size was something around 5 millimeters, and it resulted in 21,000 elements with 4,700 nodes. It's not that big number, and for today's computer it's quite simple to solve. And then what is kind of standing out from the picture is that you have some rigid beams at the end of the bones, and basically those are the places where you connect them to a virtual rotation point for doing the model analysis. So that's like preparation of the model for using it in flexible multibody simulation. Then this is a femur bone, which is the largest long bone in our body. And this one was meshed specially, so in the middle we have a more coarse mesh, because that part was not so interesting. It has something like 5 millimeters, but the distal ends have much finer mesh, including mesh which is less than half a millimeter in the neck zone, which was interesting from the perspective of stresses, because this is highly loaded part, and usually if the hip fracture is happening, this is happening somewhere there. And this model was much larger. This was 330,000 elements and 65,000 nodes. It took already some time to solve it, but today it would be quite easy to solve as well. Now, when it comes to computational load, when you have the model of the machine and you have the model of the human, you build your representation of the mathematical representation of that, and you try to solve it. You'll realize that for a man-made structure, you might have, let's say, 10 to 50 bodies, 10 to 100 joints, depending on the level of detail. And you can quite easily kind of cut your structure and just take a fraction of it and simulate. In a human, cutting part of the structure to simulate is often done, but in many cases you would need the whole structure. And what changes here is that you might have much more bodies, and you can have much more joints, and plus you might have much more complex models for the muscles, and they actually slow down the simulation a lot. And the contact models, which are almost always a necessity, you rarely can skip them. So now when you add 12,000 degrees of freedom finite element model for just one bone, you realize that this you can solve drinking a cup of coffee and you get a solution, but the other one is like really, really slow. So because of the number of degrees of freedom, especially when you add the flexible parts, you have to be careful how you do it. And one of the ways to avoid spending large time for the multibody solver or finite element solver to solve everything, you divide the work and you do the so-called model reduction. So first, you have a volume of a bone. You import it into the finite element software and you mesh it. After you mesh it, you add the material properties to the bone so that you could have the response from the bone computed later on. Then you can add, for the long bones, the beams at the end to those fixed points. And then you do the model analysis. And from the model analysis, you get different shapes, how this bone can deform under different loading. So it applies unit loading to every of these node points in all possible locations. And then it sees how the bone can be bent. And of course, there is a relation. Like if you have a beam and you apply a force in one end and the other one is fixed, then you know how it will deform. And then if you make the other fixture different, so it made a rotational joint, and you apply the same forms, again, the response is slightly different. And changing those boundary conditions, playing with them, you can generate how the structure will behave. And of course, the bending of the structure and deformation will always be related to the structure. So if you have a uniform beam and you twist it or you bend it, it will bend or twist uniformly. But if you have a shape like a bone that is thicker in some places, stiffer and weaker in the others, then when you apply different loading, of course it behaves a little bit differently, but it's predictable. So when you get those modes of bending and twisting, you can actually use them in the simulation, saving a lot of computation. So instead of solving the whole model, you use these modes, which are simplified version. Of course, this causes some loss of accuracy, but once you get the model running with that and get all the final things, then you can, if you really want to get full accuracy, run the full model just once, solving it for good. But first you can experiment with the deformation modes and get, in most cases, you will get good enough solutions even for stresses. So how does it happen? So we have the environment, we have the natural movement, verification and models, and we link them into a simulation. And what do we have as an environment? For the environment, we have exercising equipment, for example. We have human subject, which is important. For the natural movement, we can get it from motion capture. That's the easy way. You could try to do any other thing. You could use even some kind of encoder or potentiometer on the joint and just measure how it moves. That's also fine technique. And you can measure the motion from there. But anyway, you need the motion from somewhere. Then if you have force sensors and any additional sensors, that is your data for verification. On your way to get a good model, you need to get some kind of verification information, because you can start with just a computer model and simulate something and say these are the results. But then the first question from your audience will be like, how do you verify it? How you can check that you said that the force will be there, like, 100 newtons. How do you know that it's 100, not 300? What is the accuracy of your model? So you need some verification. So if you measure a few forces and you can calculate from them something that you can compare, that will give you an information so that you can verify if your model is close or far away from the reality, and how close you can get. Then there are the models. And inside the models you have the bones, you have the joints, you have the muscles, you have the contacts, and you can add anything extra that you require. So the foreign objects that collide with the human subject or interact with the human subject should be always added to the simulation. Now, once you get the simulation kind of created, so you have the human model and the motion capture, and you can merge it and do the inverse dynamics. And inverse dynamic is quite useful, because you will see that, okay, I have the puppet, and then I have the motion to drive it, and then I'm seeing how it moves. And from there I can estimate what would be the forces to actually cause this motion. So that's why it's a very common method which is used quite a lot. But the other benefit from that method, we get how this actual body is moving. So the motion capture gives me motion of individual markers, which is not meaningful really. But once I attach it to the human body and move this human body with those markers, just pulling by those markers to follow the motion data, I see what is the body joint angles. So knowing the body joint angles, it's already a useful information. Now after the inverse dynamic, I can add flexible bones. Why I cannot add flexible bones in the inverse dynamic is that in the inverse dynamic, every marker is pulling the bone in some location. So if the bone is flexible, and there's always a mismatch between the marker position, they are not 100% accurate, you will see that your markers will stretch and shrink your bones because they have actually no limits. They will have really hard springs pulling the hand, harder than the hand or the leg. And that's why you cannot put the flexible bones in the inverse dynamics. This is something that you can use in forward dynamics, where the forces applied actually should be realistic already. So when you have the human model with flexible bones, you can run forward dynamics. But to run it, so now from inverse dynamic you know what motion you're doing, so how each body joint should change its angle in every time instant. And now you have to apply the muscle forces to actually make this happen. So now you have to develop the controller that will figure out how to apply the muscle forces, how to control the muscles, so that the human model will be, for example, walking. It needs to keep the balance, not falling down. It needs to move in a certain direction with a certain speed and move the certain body mass of the subject. But once you manage to do that, you get several nice results. So first of all, you get ground reaction forces from the model, and this is something that you can verify with your measurements because they are easy to measure. You have bone strains. That's something that you cannot really measure unless you're really ready for big pain, and you do it somewhere so that nobody would see. And then you get muscle activities, which are also important from the perspective that you cannot really easily measure them. You cannot put a strain sensor on the muscle somewhere and measure what kind of force it's producing. It's rather impossible. So if you can simulate the muscle forces and get them, this is a really important information. And you get joint loads, which are also quite nice from the perspective of diagnostic and checking, for example, performance and limits of endurance of your bones and your whole body. Now these are some examples of simulations I did. And let's start with the simulation where nothing goes as it should be. So this guy was supposed to do a squat, but there's a problem that the muscles are not actually wrapping around his joints. So after they pass the point of rotation, they start actually twisting him forward. So he's doing the exercise according to the simulation. Simulation is successful. It went from the beginning to the end. But you might imagine that the subject didn't do that really, because we use actually real people, not some kind of rubber guys. And he will do some other. Maybe if he would practice yoga, he would be able to do that. But the final situation is rather impossible. So that happens a lot when you do the simulation. Usually you get it to crash quite much sooner. Now on the bottom, the other guy started exercising already. So he's lifting the weight with the leg. And you can see that the weight is moving up and down. Weight moving up and down is basically a kinematic constraint that is linked between those two things. That's just for visualization, because simulating a rope in between would be quite hard thing. And it's not necessary for the human model. But what is important here, the other guy is still falling. What is important here is that there is a contact between the foot and the platform, and he's actually pushing. So you can separate the foot from the platform as the normal guy could. And there is a flexible tibia which changes colors respectively to the stresses which it experiences. So you can see how he's loading the thing. And he's actually, his butt is actually fixed to the exercising machine in this example. That's why he's not falling down from there. So there was no need really for the full body there, but it just looked nice and it was possible. The guy up here, which is just bending the knee and applying the load, is also having a flexible bone, and then there's a contact model or a sliding joint there was, I think, between the bone and the support. And the loading was modeled as a torque applied, which would normally the rope pull from the weights. So here it is modeled as a torque. So that's how you can get around. And you can see that he doesn't have any muscles on the upper body because they are not necessary. It's basically the animation part, but the muscles were applied on the lower body. Here they are hidden for the clarity of the vision. Now the last guy who is doing this exercise, he was just for testing one thing. So he has, in addition to bones and muscles, he has also those kind of soft tissue balloons. And this was just to model the contact between his body parts and the seat. So basically how he's seated there we use only contact to keep him seated, and it's stable. Normally you would fix him, but we just attach him with a contact to see how it happens. And the actual motion that he's doing is purely artificial. It's not based on motion capture. In the inverse dynamic, there was just a bar pulling him up by the neck or something like that, or chest. And that was how we did the motion to record it. And then this motion was used for training the muscles to actually do the forward dynamic simulation with the contacts and stuff. So you can do certain tricks to get your simulation up and running, and learning how to do that, you can figure out how to build your model using some experience that you can get from there. Okay, this is walking, and this is walking from a side. You can see that he has this kind of bear-like feet, and those elements are for contact detection, and they have to be some simplification because in our simulation the foot was rigid. So normally when you have a toe off, you're actually bending your toes. You're changing the foot geometry, and here it is simulated by the balls under the toes, so they are slightly moved back so that he could actually make the toe off without dragging his feet through the floor. And that's based on recorded motion. And there was a flexible tibia, and now the other guy started walking, and he has flexible thigh. That was the thigh model shown in the previous slide. And again, we have muscles, but we are just hidden to show the stresses. And here the stresses were mostly interesting on the neck section. And of course, the guy is walking, and we can see the ground reaction forces appearing. So you can see that there's an impact always when he's landing on the heel, and then there's a little bit increased force during the toe off phase. Now here's an example of the weightlifting. Another modeling case where basically the guy was standing straight and his feet never separated with the ground. So instead of modeling contact between the feet and the ground, we actually used bushings there. So bushing elements allow to, like, are hard springs basically, so they can simulate what kind of force you need to keep him balanced. And he was able to lift the body. And he's holding the bar with the open hands because it doesn't matter when you can apply the fixed joint. And we had a rigid model of the hands. Now this is cycling on a stationary bicycle. And as you can see, you only need the lower body because that was the interesting part. And you don't need the bicycle except the crank and the seat. Seat is purely virtual here. It's actually modeled with the motion recorded. And the crank, we made some kind of a design of the crank so that it would be visible, but the actual important parts were the pedals only. The rest could be removed. But because we had the bodies modeled, then actually you could apply the joints between the pedals and the crank and everything else, and apply torque to the crank, which is the limiting torque created by the cycle. And what we did here, for example, to verify that, we put the insoles in the shoes, which measured the forces, so we knew how much the guy was pressing. And because the guy had a history of being a football player or some other sport which is kind of asymmetric, we realized that even though from motion you could not see this, he was applying almost twice as much force on one leg than the other. And actually we could also see that later on in the simulation, which was quite nice. That was very simple simulation, but it was still interesting to see how to model cycling. The feet were fixed to the pedals. They were allowed only to rotate. But because the contact was more difficult in that location. But anyway, the model was quite nice. Now these are examples of jumping and walking. And this is walking where we have just the lower body. So the whole mass of the body, in general, if you calculate your center of mass, it will be somewhere on the level of pelvis. Even though you're tall and maybe you can feel that you're well built, the center mass will be here. That's why you can actually bend forward and not fall on your face. And that's why if you put your whole body mass somewhere here and remove the rest of the body, you can still simulate walking quite well. This is a simplification because you don't have the hand motion, which is usually used to compensate a little bit and give you some stability, but it still can be done. And jumping was done in a simplified way, but there were all the bones here flexible to see what are the forces. And the guy was hopping, and his hands were constrained because we didn't have the recording for the hand motion, but he was asked to jump and they were more or less steady. So I don't have the video now from the actual motion trial, but that relatively good. And jumping is quite difficult because of the landing. I mean, jumping is the easy part, but then when you land, you have to keep the balance. And that's a challenge. Now, there's another example that you don't have to really apply it to the human only. So I played with Savannah Monitor, which is quite a big lizard. Quite many people use it as pets. It's the size of a cat, you could say. But it can be quite fast, also like a cat. And there's no protocol how to attach marker to that kind of animal to measure the motion, so I had to figure out the protocol to do that. And I was first wondering whether the animal will allow to attach the markers on the double-sided tape, but he didn't have anything against. And they walk in a funny way because they drag their belly. They can actually have this high or low level walking. So when they have the low walking, they drag their belly and they just move their feet. And they have also, like the crocodiles, they can have also the high level walking where he lifts off the belly. So it's very challenging to measure anything from that kind of animal, especially that when he's walking and you would like to have a ground reaction force after on every leg separately, you would have to have really tiny force plates and lots of them, because you cannot control him like a human. With the human we say go straight, and the human is going more or less straight as long as he's not drunk. But with the animal we put it on the floor and expect it to go where we want it to go. And trying to give him food is not even something that we haven't even tried, because then we would not get walking, but we would get like a rocket running, I'm guessing. And it was also quite funny that he didn't like the force plates, because they were metal and they were cold, so he was walking everywhere around them. And he has quite complex walking style, and then there's a video of how he's walking. So we made the lines so that he would know where to go, but he didn't really follow them. And there are force plates in front of him which are quite big compared to his size, but we were hoping that we would get at least partial ground reaction force for 1 or 2 steps so that he would walk on them. And once he put his foot on that, he realized that, oh, it's not so nice as the wooden floor, so I'm going around. And this is one of the successful trials. And we wanted him to go straight, but for some reason he was so curious that he didn't want to walk straight, and at some point he just climbed on his cage and stayed on there. He was very cooperative, surprisingly, but I don't know if it's very visible from the video here, but when he's walking, he's doing something like, he puts the foot on the ground, then moves forward, and then moves something like that and drags it back. So this made it impossible to put any marker on the top of the foot. So then to know the orientation, we only had to have a marker on the side, which sometimes he also managed to get off just by accident. He didn't even try to remove it, but we cannot attach it with a super glue because we need to remove it at some point. And it's really challenging to do any sort. Maybe elephant would be easier because it's bigger, so the markers would be more far away from each other. But still he could shadow some of the markers with his big body. And now this is the same model done in MATLAB with the walking. So here we have a visualization of his skeletal system with just some stick figures and the numbers which correspond to the markers. And that's the top view from his walking. So that much was possible with that kind of data. And the data had a lot of things to correct. So after we got the motion data from several trials, we had to actually glue together some of them to get some walking cycle, and it's really, really complex thing. Now if we think about the results for the human, so for normal walking, we have few phases of walking. So we have heel strike, then we have the toe off when the foot is moving forward. We have also forward swing in between. And then we can also look at the double support and single support phases. So double support when both legs are on the floor, single support when one leg is up. And this requires balancing. So that's a little bit complex in walking, that when you're walking, when you stand on 1 foot, for example, for a second, you actually have to move your balance to that side. And then when you're landing on the other one, you're shifting the balance. And you try to do it somehow softly. And trying to model it is a little bit complicated. But from the flexible tibia, we got the strain results, and they are expressed in microstrain. And once what we could see is that you can see that half of the bone is in compression while the other one is in tension, more or less all the time. So basically what happens during the heel strike and toe off. This is scaled to match the picture more or less. So you have a heel strike, you have bending, then you have a toe off, you have bending, and then when the leg is in the air, basically they are just inertial forces and some residual muscle forces that are bending the leg. But the leg is bent most of the time during walking. Of course, it's compressed, and you can see that the whole thing is kind of shifted towards the compression, but the dominating load is bending. Now for the knee flexion, we tried with 25 kilos, and we asked the subject to do it with 3 different speeds. This was actually, we haven't thought about that there might be a problem when you ask the person to move slowly and medium speed and fast. So slow and fast is easy, the binary logic, but doing something in between, it either gets closer to fast or closer to slow. It's difficult for people to kind of figure out it in the middle. But you can see how the force is actually changing in the knee, depending how you do the same motion. So if you do it slowly, you get a lot of jaggy elements, and this is because you're muscle twitching, because you're fighting with the load, and you're trying to maintain some velocity and some position, and our control system is not the fastest one. So that's why we just apply force in one direction and in the other, and we try to compensate. Where you do it fast, you get a smooth curve, because you just apply the force, and then you apply the braking force on the other side, and that's more or less how you do it, and how you change the loading. Medium, as I said, is something not very conclusive, because it's difficult to tell how close it was to medium and how close it was to fast. Now, if you do the extension, so the exercise with the force applied in a different direction, you have completely different force profile. And here, when you do it, trying to do it slowly, resulted in that when you get close to turning point, there's some impulse when you try to slow down, not to hit the limit. And when you do it fast or medium speed, you did not create this excessive force for braking. So in that case, you would say that if you do it relatively smoothly, and fast doesn't mean that you try to do it full speed that you can, but you just try to do it in a way that you don't feel like you're trying to make it really extra slow. So if you do it the natural motion, you actually kind of optimize it to avoid excessive loading. Then there were some kind of comparison of those results, that subjects said which one was more difficult to perform with the different speed, which was easier, and what was the sensitivity to the joint forces to speed, and what were the peak strains in the bones. And these were 2 exercises compared here. So I hope that this is a good introduction for you, just to give you some kind of overview of what you can do. What are the difficulties? What are the tools? What are the methods that you can use? And what you can get out of the kind of studies? And if you get interested in future, then I hope that you'll get some projects to work on the biomechanics, because I can admit that it's a very interesting topic. There's lots of interdisciplinarity there. You have to consult with different people. The fact that you have to combine experiment and simulation already puts some kind of constraint that you have to kind of understand how the experimental work is done and what are the problems with experiments and how to solve them. And the fact that you have to work in simulation is also giving you some kind of information to play with computers a lot. And if you have a good ideas, then you can simulate really complex things, and you can use even high power computers for doing the work for you. But it needs a lot of additional studies to learn how to use them really. So thank you very much, and if you have any questions, I'll be glad to answer. No questions at all? Okay. So then I guess you're free, and then have a nice weekend exams coming, and hopefully you'll get interested in the topic. So thank you very much for your attention.